Hello everyone! Let's talk about something that powers almost every piece of technology you use every single day. I'm talking about semiconductors. Think about your smartphone, your computer, your television, and even the lights in your home. Deep inside, all of these wonderful gadgets are tiny electronic components that make them work. The heart of these components is a special kind of material called a semiconductor. It's not quite a conductor, like a copper wire that lets electricity flow freely, and it's not quite an insulator, like rubber that stops electricity completely. It's somewhere in between, and that's its superpower. We can control exactly how much electricity passes through it, turning the flow on and off like a super fast light switch. This on and off switching ability is what makes all of modern electronics possible. These tiny switches are called transistors, and they are the fundamental building blocks of computer chips. By arranging billions of these transistors in complex patterns, we can create processors that perform calculations, store memories, and run all the apps and programs we love. The most common semiconductor material used for this has been silicon. For decades, engineers and scientists have been on a quest to make these silicon transistors smaller and smaller. Why? Because the smaller they are, the more you can fit onto a single chip, the faster they can switch, and the less energy they consume. This continuous shrinking is what we call Moore's Law, and it's given us the incredible technological progress we've seen in our lifetimes. But we're starting to reach a limit with silicon. As we try to make things smaller and smaller, we run into some tricky physics problems. It becomes harder to control the flow of electricity, and the transistors start to leak energy, which makes them less efficient and produces a lot of heat. Think of it like trying to build a faucet that's so small, it can't fully shut off the water. It just keeps dripping. This challenge, often called the end of Moore's Law, has pushed scientists to look for new materials and new ways of building these essential electronic components. The future of technology depends on finding a way to keep making things smaller, faster, and more powerful, which means we need a revolution in how we think about semiconductors. This is where the world of nanoscience comes in. We're not just talking about making things small, we're talking about making them incredibly, mind-bogglingly tiny, at the scale of individual atoms and molecules. A nanometer is 1/1,000,000th of a meter. To give you some perspective, a single human hair is about 80,000 to 100,000 nanometers wide. Scientists are now building transistors that are just a few nanometers across. At this tiny scale, the rules of physics start to change in fascinating ways. We can harness these new rules to build devices that are far more advanced than anything we've created before. It's a whole new frontier in electronics, and the discoveries being made today are paving the way for the next generation of technology. So, how do we get around the limits of silicon? By exploring new materials and new designs. Recently, brilliant researchers have been making incredible progress with what we call nanoscale three-dimensional transistors. Instead of building flat transistors on a chip, they are building them vertically, like tiny skyscrapers. These transistors use nanowires, extremely thin wires only about 6 nanometers in diameter. That's unbelievably small. To make these new devices work, scientists are turning to different elementary semiconductors, such as gallium antimonide and indium arsenide. These materials have special electronic properties that make them much better suited for building extremely small, high-performance transistors than our old friend silicon. What's really amazing about these new transistors is how they work. They operate based on a principle from the bizarre world of quantum mechanics called quantum tunneling. Instead of needing to push electrons over an energy barrier like a traditional switch, quantum tunneling allows electrons to pass right through the barrier when it's thin enough. Imagine trying to get a ball over a tall wall. Classically, you'd have to give it enough energy to go over the top. But in the quantum world, there's a small chance the ball can just appear on the other side. This means these new transistors can be switched on with much lower voltages, which saves a tremendous amount of energy. This energy efficiency is a huge deal. One of the biggest problems in modern electronics is something scientists call the Boltzmann tyranny. It's a fundamental limit on how little energy a conventional silicon transistor can use to switch on and off. But these new gallium antimonide and indium arsenide transistors can break past that limit. They can perform just as well as the best silicon devices we have today, but they do it while using significantly less power. This means future devices could have batteries that last much, much longer, and data centers could run with a fraction of the electricity they currently consume. It's a game changer for creating more sustainable and powerful electronics. The performance boost is also remarkable. Early versions of these types of tunneling transistors were often slow and couldn't carry much electrical current. However, these new three-dimensional nanowire designs are different. They have been shown to achieve a drive current, the amount of electricity they can push through when they are on. That is about 20 times better than previous tunneling transistors. This combination of high performance and low power consumption is exactly what the technology industry has been searching for. It represents a major leap forward, showing a clear path to continue the incredible miniaturization and advancement that has defined the digital age for the past half-century. Beyond building better transistors, scientists are also finding new ways to control the materials themselves at the nanoscale. Think about it. If you can precisely control the electrons in a semiconductor, you can change its properties on the fly. Researchers have developed an incredible new tool to do just that. They use a device with an extremely sharp tip, part of an atomic force microscope, to deliver tiny electric pulses to an atomically thin layer of a semiconductor, like molybdenum disulfide. These pulses are incredibly short, lasting just 30 nanoseconds, and they can be used to push electrons out of a very small, specific area, creating a temporary depletion region. This technique is like having a microscopic pen that can draw and erase patterns of electrons on a two-dimensional surface. What's so powerful about this is that it's all electrical, dynamic, and reversible. You can create a pattern, see how it changes the material's optical properties, like how it glows when you shine a light on it, and then erase it and draw a new one. Before this, methods for changing electron density at the nanoscale were often imprecise and permanent. This new method gives engineers an unprecedented level of control, allowing them to fine-tune and engineer the properties of a material in real time. It opens up exciting possibilities for creating advanced optoelectronic devices, like highly efficient light sensors or new types of displays. And the world of nanoscale semiconductors isn't just about making electronics faster and more efficient. It's also about making them healthier and safer. Consider this. What if the screen of your phone or the surface of a medical device could clean itself? Scientists have developed a new type of nanoscale semiconductor with antibacterial properties. They started with a material called antimony selenide and introduced silver atoms into it using a clever chemical process. This creates a new, layered material that has a fascinating ability. When you shine visible light on it, it becomes a germ-killing machine. This antibacterial action happens through a process called photocatalysis. When light hits the surface of this new silver-doped antimony selenide, it excites electrons and creates highly reactive molecules that can destroy bacteria. In experiments, this material was able to completely inactivate a common bacteria, E. coli, in just 2 hours under normal light. This technology could be revolutionary for public health. Imagine coating hospital surfaces, medical instruments, water purification systems, or even doorknobs with this material. It would create self-disinfecting surfaces that work continuously, helping to prevent the spread of infections without the need for harsh chemical cleaners. It's a brilliant example of how material science can solve real-world problems. So, what does all this mean for us? These breakthroughs in nanoscale semiconductors are not just small steps. They are giant leaps that point toward a future that looks very different from today. The development of ultra-small, energy-efficient transistors using materials like gallium antimonide and indium arsenide promises to keep our technological progress accelerating. It means we can look forward to electronics that are not only more powerful, but also much kinder to our planet's energy resources. Your future smartphone might run for a week on a single charge, and the massive data centers that power the internet could dramatically shrink their carbon footprint, all thanks to the quantum-level magic happening inside these tiny components. The ability to dynamically control electron density in two-dimensional materials will also unlock a new generation of smart devices. This isn't just about faster computers, it's about creating new kinds of technology we've only dreamed of. We could see flexible, transparent electronics woven into clothing, or ultra-sensitive sensors that can detect diseases from a single drop of blood. By being able to precisely engineer how a material interacts with light and electricity at the most fundamental level, we are opening a toolbox for innovation that will impact fields from telecommunications to quantum computing. It's about creating materials that are not just static components, but active, tunable systems that can adapt to our needs. Furthermore, the creation of antibacterial semiconductors shows that this technology has a profound role to play in our health and well-being. In a world increasingly concerned with hygiene and preventing the spread of disease, self-cleaning surfaces represent a powerful passive defense. This technology could make our hospitals safer, our public spaces cleaner, and our water purer. It's a wonderful fusion of electronics and biology, where the properties of a semiconductor are harnessed to protect human life. This moves nanotechnology beyond the realm of gadgets and into the critical domain of global health, offering sustainable solutions to persistent challenges. Ultimately, these revolutionary nanoscale semiconductors matter because they address some of the biggest challenges of our time. They offer a path to more sustainable technology, more powerful computational tools to solve complex problems, and new ways to protect our health. From the quantum tunnels inside a 6-nanometer transistor to a self-sanitizing surface activated by light, we are learning to build a better world from the atoms up. This isn't science fiction, it's science fact, happening right now. And it's going to make our future smaller, faster, smarter, and a whole lot healthier. Consider that.